In this class, we are going to talk about energy policy, but we also need to talk about the physical processes of production and consumption of energy. So this short lecture is on the topic of what is energy. The physics version is energy is the ability of a physical system to do work. So if you've taken a physics class, you will have heard of that before. Energy is a property of objects that can be transferred to other objects or converted to other forms. So energy is neither created nor destroyed, it's only transferred or transformed. So coal has inherent energy in it, and we're transforming that energy into something that's useful for us. The economics version is slightly different. Energy includes all energy resources and energy commodities that can be used to provide energy services. So energy resources from an economics perspective include non-renewable resources like coal, natural gas, uranium for nuclear, crude oil, etc. And renewable resources are things like hydro, wind production, solar panels, or geothermal. Energy commodities are things like electricity, gasoline, propane, diesel, natural gas. These are things that you can purchase on the commodity exchanges, and you can purchase futures for these and whatnot. And they're fungible goods, meaning that gasoline in one part of the United States is the same as gasoline in another part of the United States. Same with oil. And that's why we have a global oil market, because oil is fungible. It's transferable. Energy services, the things that energy provides, are things like lighting, cooking, and transportation. So we have to think about, when we think about energy, we have to think about all the types of things that we use energy for. We use it to drive our cars, to move ourselves around, to light and heat our houses, etc. The standard unit of energy is the joule. The symbol of this is a J. A joule is the amount of energy transferred to an object weighing 1 kilogram when it is accelerated at 1 meter per second squared over a distance of 1 meter. Okay, so what does that mean? That's roughly the energy transferred to an object weighing 1 kilogram by lifting it 0.1 meters. So the amount of energy it takes to lift a 1 kilogram object 0.1 meters. 1 kilogram is roughly 2.2 pounds, and 0.1 meters is roughly 4 inches. A calorie is the amount of energy required to heat 1 gram of water by 1 degree Celsius. 1 calorie is exactly 4.184 joules. A joule measures a tiny amount of energy. So we'll be talking about transfers of billions and trillions of joules, and so we need to think about scientific prefixes. For example, the kilo or kilo symbol is lowercase k is 1,000. Mega symbol is uppercase M, which is 1,000,000. Giga, uppercase G, billion, and tera is trillion. 1,000,000 joules is a megajoule, or an MJ. The symbol for kilo is a small k, while the others are capitals. What is power? Power is slightly different than energy. Power is a measure of the rate of energy transfer, or it's often confused with energy. We'll talk about power when we talk about kilowatt hours, or energy used over a specific amount of time. One way to keep them straight is to think of them as analogous to speed and distance. Speed is a rate of change in distance. For example, 60 miles per hour, which doesn't necessarily mean you're going 60 miles, it just means you're going 60 miles per hour. If you traveled for 1 hour, you would go 60 miles. To calculate the total distance traveled, we would multiply average speed by the time taken. So if you travel 60 miles per hour for less than an hour, anyone that's driven a car knows that you're not going 60 miles, you're going to go some fraction of that. So a car traveling 100 miles per, that should say mph, for 5 hours will travel 100 miles. The standard unit for power is the watt. So when we talk about electricity, we're talking about watts. 1 watt is defined as 1 joule per second, J over S. The amount of energy transferred by applying 1 watt over a period of 1 hour is a watt hour. This is very useful. It's a very useful unit of energy. How many joules does 1 watt hour equal? You should ask yourself that question. A watt hour is still a small amount of energy. A kilowatt hour is 1,000 watt hours, or 1,000 times 3,600 joules. And the unit for a kilowatt hour is the small k, capital W, lowercase h. So when we talk about power consumed in a home, we'll typically be talking about kilowatt hours. Power produced by generators is typically denoted in megawatt hours. An important note about units: a watt hour is a unit of energy. We define it by multiplying a rate, energy per unit of time, by an amount of time, an hour, so that time units cancel out and we're left with a measure of energy. The unit is watt hour, not watt over hours or watts per hour. So we should be clear when we're writing this down that if we say 17 watt hours, it's not 17 watts over hours. So getting the units correct is important. Here are some practice questions for you to do, and you'll do a short quiz with similar questions to these after you see this little lecture. So suppose we start with a 1,000 milliliter bottle of water, that is 1 kilogram of water, at room temperature, or 21 degrees Celsius. What is the quantity of energy in joules that is required to bring this water to 85 degrees Celsius? So things we know, 1 calorie equals 4.184 joules, or energy required to heat 1 gram of water to 1 degree Celsius. To find the answer for 1 gram of water, to heat it to 85 degrees from 21 degrees, we have to figure out what's the change in degrees we're going for. So 85 minus 21 degrees C times 1 calorie over 1 degree C times 4.184 joules over 1 calorie gives us 267 joules. And for 1 kilogram of water, remember that's 1,000 grams, so we multiply this by 1,000, equals 267 kilojoules. Question 2. What is the quantity of energy in kilowatt hours that is required to heat the bottle of water to 85 degrees? So now we want to convert our previous calculation to kilowatt hours. We know how many kilojoules it takes, so let's convert it kilojoules to kilowatt hours. So 1 watt hour is equal to 1 joule over per second times 3,600 seconds per hour equals 3.6 kilojoules. Therefore, 1 kilowatt hour equals 3.6 megajoules. 267 kilojoules equals 0.267 megajoules. So we can find how many kilowatt hours we are using with the following equation. X kilowatt hours over 0.267 megajoules equals 1 kilowatt hour over 3.6 megajoules. And then let's solve for X. And if we do that, we get 0.074 kilowatt hours. And that's our answer. Our electricity is billed in kilowatt hours, and the marginal price of electricity in Fort Collins is 13 cents per kilowatt hour. So based on this price, what's the cost of electricity used to heat the bottle of water to 85 degrees? So this is fairly simple. If electricity costs $0.13 or 13 cents per kilowatt hour, then 13 cents per kilowatt hour times 0.074 kilowatt hours equals approximately 1 penny. So it costs about 1 penny every time you heat a liter of water. Question 4. So now we're going to bring in this fictitious person, Eric. And let's suppose Eric is concerned about the environmental and financial cost of his electricity use. Each day, Eric heats a 1 liter bottle of water to make 4 cups of coffee. And Eric decides to replace his 800 watt kettle with a should be larger kettle of 1,370 watts. By how much will this change Eric's monthly electricity bill? What else will change for Eric? The first thing we need to know is that the amount of energy required to heat the water bottle has not changed. This is a physical problem, heating the water bottle, so we can't change the amount of energy required to do so by simply changing the kettle. What will change is the amount of time it takes to heat the water. So we still need 0.074 kilowatt hours or 74 watt hours, but the time it takes to heat it will change. So let's do this calculation. Before, Eric had an 800 watt kettle, and we multiply that by X hours to get 74 watt hours. Now we can solve for X again, which results in 0.0925 hours, and then we'll convert that to minutes. So with an 800 watt kettle, it took about 5.5 minutes to heat it. Afterwards, he's going to have a 1370 watt kettle. We can solve for X again, and that turns out to be 0.054 hours, and then converting that to minutes, he's down to 3.24 minutes. So a stronger kettle with more power reduces the amount of time it takes to heat the bottle, but it doesn't, of course, change the total amount of energy it takes to heat the bottle.